In this lecture, we're going to talk about consolidation and settlement. And the two terms are describing the same thing, but they describe them in a different way. I want to talk about what those ways are. But let's just go ahead and get started. Soil is a non-homogeneous porous material consisting of three phases: and solids, fluids, and air. Normally water, fluids. And we discussed this in soil composition. Soil deformations can occur by changes in stress, water content, soil mass, and temperature. And we've seen what water content can do with effective stresses and capillary rise. And that's going to become even more evident as we get deeper into the material. Temperature, somewhat, not too much, because the temperature in the earth is fairly consistent unless you've got a volcano erupting or something like that. If you have put a foundation on the soil and the soil deforms below you, it is referred to as settlement. And as I've said before, settlement of soils below foundations is the most common cause of foundation failures. We think about, we're going to look at examples in this course in foundations on catastrophic type of failures, but settlement failure is by far the more common. It may not be as catastrophic, it may not be as spectacular, but it can be very expensive. There are three types of settlements. Elastic settlement is settlement due to immediate elastic deformation before major particle rearrangement. Primary consolidation settlement is settlement due to major particle rearrangement. And secondary is further particle rearrangement after primary settlement. That's about the simplest way. And traditionally in soil mechanics, we add the three together. That's the traditional approach. And I've taken a little bit different approach. Remember the last time we talked about elastic settlements, mostly in terms of IGMs and rocks. And you can use them, but we're going to take a little bit different approach with this particular, in the fact that we're going to concentrate on settlement rearranging for classical soils, particularly looser soils. In other words, the looser the soil, the more potential there is for particle rearrangement type or settlement. In clays, that's consolidation type settlements. It sands is a little different. Other types of settlement, there are other types of settlement, such as dynamic forces, which actually compact it by vibrating the soil in some way. Expansive and collapsible soils, we'll talk about that in 4610. Settlement and consolidation. Volume changes in soils are not instantaneous. They take place over time. The question is how much time. Depends upon the soil and its permeability. Primarily its permeability is the big variable. Now, let's stop and define two terms. We're going to come back to this. Settlement and consolidation describe the same thing, but they describe it in a different way, and they answer different questions. Settlement refers to how far does it go? What distance does the structure move? What distance does the soil compact under it? Consolidation has to answer the question, how long does it take to get from the point A to the point B we figured out in settlement? And those are the two questions that we attempt to answer with settlement and consolidation theory. The rate is, again, how long it's permeable. I kind of repeat myself in this slide, but repetition is the essence of education. It depends upon the permeability. Normally we're talking about for classical consolidation problems, we're always talking about saturated soils. With other types of particle like rearrangement with cohesionless soils, not necessarily. Cohesive soils are, because of that, because to what happens in a consolidation process is that you reduce the void ratio or the porosity in a soil, and when you do that, you by doing that, the voids have to. If the voids have air, there's no big deal. But generally speaking, with the saturated soil, the voids are going to all have water. The water has to come out. If you've got a low permeability soil, the water will come out slowly. If you've got a high permeability soil, it'll come out much more rapidly. That, in a nutshell, is what you're dealing with here. So cohesionless soils are more rapid. We're going to talk about two methods to determine. One of them is Huff's method, which in this course, and then Schmertmann's method in the next one, which tries to combine more of a theory of elasticity approach to this overall for cohesionless soils. And we're going to talk about that. I'm going to come back to that in just a minute. The principles of consolidation is difficult to understand in many ways. It takes a little thinking. Basically, I see this spring thing that your the Soils Foundation's handbook has is a classical type of analogy people use. I'm not sure if I found it very helpful, but let me try to. It's really more like a sponge. Let me explain. We start out with a soil, and I draw a phase diagram, saturated soil. We're going to talk about cohesive soils primarily first, because cohesive soils have been the biggest problem. You always hammer down the nail that sticks up the furthest, and cohesive soils have been that nail for many, many years. You start out with a cohesive soil with soil particles, solids, and water. If you put pressure on this, the water is sooner or later going to come out. In the cohesive soils, that usually is later. Sooner or later, that water is going to come out of the soils. It'll seep up through the pores and leave. But the end result of that for settlement is that the void volume decreases, and because the water is out. And this little diagram shows that the primary settlement that we have in soils is equal to, can be related to, the change of the void ratio times the thickness of the layer. And we're talking about one-dimensional consolidation, which is all in one dimensions, divided by 1 plus the initial void ratio. That's a key, particularly in U.S. usage, because in U.S. usage, we like to use void ratio to do that. And that's and Scandinavian, by the way, does it the same way. It's the Voigt and the Dutch and a lot of them that do it differently. But this is the basic. You're basically starting out with a high void ratio soil, and you end up with a low void ratio because you've compacted the particles together, you squeeze the water out. So that's pretty much what you have with and that is consolidation settlement in one shot, and it gets more complicated after that. So let's talk about the consolidation test. A test, the idea of the consolidation. Now, these layers and soils of clays are thick, several feet or meters thick. And obviously, to take a whole layer out and try to test it would be difficult. So we do it in a miniature. And basically, a consolidation test is intended to replicate the process of primary and also secondary settlement and consolidation. You have to have an undisturbed specimens, which was always the bugaboo when we ran it in our labs, as the disturbance will change the soil skeleton structure and thus the result. Now, after that, you have a consolidometer. Has a rigid base, porous stones. You've basically got a base to it. It has two porous stones. The sample is a cylinder. You have two porous stones, one above and one below. Double drains, we'll talk about that. and we put a weight on it. The one shown here is your classic, beam consolidometer, where it's got a weight on the end of it down here. Newer ones use sometimes air pressure to push a piston down. The advantage of the air pressure is that you could actually run the test completely remotely without having to run in every 24 hours and put more weight on this thing, which is the way we have done in our lab. Consecutive loads on the specimen, we do it, basically what we do is we have a series of loads, and normally it takes 24 hours per load. In other words, you put, we take the force, do the little beam thing in statics, and you divide you come up with a first set up for half a KSF, then 1 KSF, and all the way up to 32 KSF on this specimen, which is standard size. For each day that you run the test, or each load, for each day you run each load, you record the movement of the top piston downward, which is the compression of the specimen, at fixed time, 0.1 minutes, 0.2 minutes, that sort of thing, all the way down to 24 hours. And then when 24 hours is done, you put the next load on it, you increase the load, and you keep going until you get to the end. At which point you've accomplished two things. You've accomplished, you know how much it settles for a load, and you know how long it takes to do it, and then you extract the data. At this point, we have a Voigt shows that the results are, generally speaking, can be plotted on our log results. Can be, actually, it's semi-log, actually, excuse me. It's log this way and non-logarithmic. That's a semi-log results. You can plot semi-logarithmic, and you get a straight line, which basically, if you use a standard stress, a stress-strain type of approach, you get this type of equation with a natural log of sigma, which is the stress at a given point, where sigma naught is the ratio of the stress at a given point to the stress at the beginning, which is sigma naught. Sigma naught normally means, but not always. It can be arbitrary. Where you start an effective stress. It usually means the effective stress that you find out. We'll get into that shortly, but it doesn't have to. But anyway, the sigma naught, if you get for an unpreviously consolidated sample, you get a nice straight line in a logarithmic plot. You'll notice that Voigt does two things. First of all, he uses a natural log here. Now, for some reason, until recently, the geotechnical community has had an allergy for natural logarithms. But Voigt, you can actually, of course, convert by just simply using a common log. You'll get the same thing. What will change, however, is this constant, which is the C or C10 constant, C being the constant for natural logarithms and C10 being the constant for common logarithms or base 10 logarithms. But notice that he has epsilon, which is a strain, is equal to 1 over C10 times this logarithmic ratio. And that is very common the way they do it. Of course, the game plan you're trying to do in this type of test is to determine that C10 value. Generally speaking, in the U.S., we use a Voigt ratio type of relationship, and we arrange the constants a little differently. However, I'm going to show you that when we get to Huff's method for cohesionless soils, where you use another particle rearrangement, we actually use a relationship that looks like this. For cohesive soils, we do something a little different. We do a lot of rearrangement because we basically translate the strain relationship into a Voigt ratio. I think I showed you earlier that why that is because the void ratio and the strain are directly related by this relationship. And so he replots these results, and he also reverses the axis. He puts the stress increase on this axis, and the strain or the void ratio, depends on how you want to plot it. We normally plot with void ratio over on this side. That way. And we end up with he first does two things. First of all, by doing this, he writes this with his strain is equal to another C sub C over 1 plus E naught. And that's what normally we're, the initial void ratio times the log of that pressure ratio. And we can actually have an equivalent between the two, between the C10 system that he likes to use and the void ratio of C sub C that we like to use. And again, we're going to see that we're going to be able to do both of them. So primary consolidation settlement involves doing applying a load onto a compressible stratum, a saturated compressible stratum, and as the pressure stays there, the void ratio decreases, and the thickness of the layer decreases, and we have settlement. And the classic relationship, we do a little more math rearranging. Basically, we say that the strain is equal to the change of height over the height. And we do a little rearranging, we get this relationship, which is the key relationship right here. Delta H, the change of that height of that layer, is equal to, because strains don't, C sub C times the initial height of the layer over 1 plus the initial void ratio layer times the natural log of this ratio. Basically, P naught is the initial pressure, or usually the effective stress. And for our computational purposes, that will be in the center of the layer, right in the middle. And then they would, the center of the layer, usually we have the average, and that's where your average effective stress. And this is something that students kind of get stumped on, because the initial stress of the layer is the average effect before anything else is applied to it. And then from there it settles. And delta P is the change that we actually induce, or whatever pressure we put on the top. And that pressure can be due to a number of factors, and we're going to look at that, how that works. P naught plus delta P is from the old pressure plus the added pressure makes us the new pressure in the middle of the layer. In the middle of the layer, average effective stress, average stress. That's what we're talking about. Not the one at the top, not the one at the bottom, the average. And that's pretty much the explanation for this slide. And that's what I've just done for you been through already. That's basically the same equation that's in your Soils and Foundations manual book. And the settlement, and the reason why they put it in this form is because if you've got several layers and you start out with the you've got several layers, the settlements are additive. Consolidations, time, a little different, but settlements are additive if you have more than one layer. Most of the problems we're going to deal with in this course have one layer. Notice that they've defined the variables carefully: the initial void ratio, the layer thickness, the compression index, the initial effective stress at the center of the layer, just like I told you, wasn't blowing smoke in your face again. And last but not least, the piece of F, the final effective vertical stress at the center of the layer, which is the initial plus whatever we apply to it. And that, in a nutshell, is the settlement equation we use. Now, the tricky part is determining C sub C, the compression index. And we can do that if we do a laboratory test. That's one of the things we get out of the laboratory test is C sub C. There are other ways of getting estimates of that. These are in your book. There are several depending upon the type of clays. I will note to you that the most common and the one that I think appears in your FE exam cheat sheet is this one right here. And this is the one that I normally expect you to use if you don't know anything else. That's one thing. The other thing I want you to note is this. We've started all our diagrams up to now from some kind of origin point, but that's not where you usually start. Generally speaking, when we put a consolidation specimen in and we run the test, we do not have a we may think we know the effective stress, but we're not really sure. So we start, say, back here, and we run up to the point where you'll get a knee in the curve, and finding that knee is an interesting aspect of soil mechanics. Beyond that, up to that point, the soil has really we've taken the soil out of the ground and we've relieved the effective stress, but the particles were traumatized by the fact they were packed together by the effective stress. And they have not recovered from that, and hopefully you can get to the lab fast enough so they won't recover from it. And then you start testing, and you get to a point where you get this right here, this knee right here, and then you get into what is traditionally called the virgin compression range, where it has never, and you have to use terms like always and never carefully, but it has not been previously stressed. And actually, it would make sense that once you get into a new range of stress for the soil, that it will actually compress more. And actually, the slope of that on a logarithmic scale is C sub C. And we actually get that kind of curve out of the compression test because of the progressive loading of it. Now, let's take an example. We have this 10-foot by 10-foot square footing, and assume due to 130 kip axial load. Assume that the gravel layer is incompressible. Well, basically what we're going to assume is that we're not going to worry about the gravel layer's compressibility. Find out the settlement of that due to the normally consolidated clay. And I'm going to talk about why normally consolidated is important here in just a bit. First, you compute the overburden pressure at the center of the clay layer. Now, there's a number of ways of doing it, and your book does it by basically the water table is conveniently located here, which is a good thing, which means that there's two ways to do this. One of them would be to do it the way they've done it, where they do from here to here. You have the total stress, there's no pore water pressure, and then from here down to the middle of the layer, an additional 5 feet down to the middle. And by the way, this is example 8.8-3 in your book. And that's how they determine it. The other way to do it, the formal way to do it, maybe if you want to, is to do the whole P0 diagram thing and start with 0, and then the total stress here will be at 14 times 130, and then and then there's no pore water, so minus U is 0, you'll get effective stress here. Then you go another 10 feet, where it is 5 feet. Now they use the submerged unit weight. That's what you're given. If you're given the submerged unit weight, you don't worry about the water. We talked about that earlier. And then you run times 65 times 10, you get additional, and then you take the average of the two. You can do it either way. Whatever way works, both of them are acceptable and get the same result. Okay, that's P0. Because we're trying to fill in, our goal is to plug and chug this thing. knowing that there's only one layer, so the summation is from 1 to 1. Delta P. Now, they use the 2 to 1 method. And I'm not going to go back through the 2 to 1 method. We just talked about it here recently. I'm not going to go back to the 2 to 1 method other than to say that they're using the 2 to 1 method, which is a little simpler from a computational. One thing you got to be careful about with the with any method, whether it's Boostenesque or 2 to 1. 2 to 1 is a lot simpler. Notice and it's easier to see with the 2 to 1 method. Notice that I said this was a 10-foot by 10-foot square, and that's sure enough 10 feet. Basically, what they're doing is they're using the formula for the rectangle, which is b plus c times l plus z, and they're basically saying, well, since b is equal to l, it's b plus z squared. That's fine. All right, it's 10 feet plus 15 feet. How do they get 15 feet? Well, there's 10 from this level here down to the middle of the layer is 50. It's 10 feet from here to the bottom of the gravel, and then another 5 feet to the middle. That's 15 feet. One thing you have to be very careful about with these problems, most shallow foundations, in fact, well, it's the exceptional shallow foundation that is done on grade. In other words, it's the surface. It's easy. You obviously have to compute your effective stresses from the surface, but you don't have your the stresses the foundation induces. The delta P starts at the base of the foundation, and the base of the foundation isn't always the surface. It's usually below it. So don't get this messed up. Just because you went down 19 feet to get to this doesn't mean you use 19 feet to get that. You start from the bottom of the foundation. The bottom foundation here is 15 feet. So you do all those computations. You come up with an additional stress of 208 PSF. Use equation 7-2, which I just showed you, to calculate that. You just plug and chug. You notice that C sub C was given to you here. Sometimes you'll get C sub C. Sometimes you'll get Atterberg limit results, in which case you would use one of these. You're almost inevitably given, you can be given an initial void ratio. You could also be, usually you're given an initial void ratio. But it's also possible you have to give a unit weight of the soil. You have to compute, in a specific gravity, you have to compute the initial void ratio, which goes back to your face diagram results. You do that, you just plug in there. The initial void ratio goes there. This comes from right here. That comes from right there. And this comes from right there. And you just plug and chug, and you get about 1.1 inches of settlement, which is nothing to sneeze at. But it could be worse. And that is the solution to this problem. Now we talk about over-consolidation or pre-consolidation. And I kind of brushed through this a few minutes ago, but now it's time to be serious about it. Basically, what over-consolidation talks about is the analysis, basically how that happens in this way. I mentioned earlier that if a soil has had an effective stress and the particles have been compacted by that effective stress, the particles have been traumatized in the past, to use a psychological analogy, and as a result, they carry that memory in themselves, and that memory persists until you get past the effective stress with the applied stress in your consolidation test, at which point they are stressed beyond that into a new territory and they are further compacted. In over-consolidation or pre-consolidated soils, somewhere in the past, the soil has been subjected to a high overburden or surcharge, and it has compressed the sparkles together, and they have been traumatized to the point where when the overburden disappears for whatever reason, the particles stay together and they don't expand back either at all or fully. An example of that, probably the easiest one, is the glacial tilts you see in the Midwest, where large sheets of heavy ice rolled over them and sat there for many years and compressed them, and then the ice age ends, they roll back, but the particles don't expand themselves, so they're still traumatized by the event and they stay together, and that's referred to as pre-consolidation or over-consolidation. And it complicates the settlement analysis of soils that are over-consolidated or pre-consolidated. You see both terms in the literature and in practice. The over-consolidation ratio, or OCR, is equal to the stress that they experienced at the point of their previous consolidation, and that they haven't gotten over that, over whatever effective stress they experience now. And if the OCR is greater than 1, the soil is considered over-consolidated. If OCR is around 1, it's normally consolidated, and if it's less than 1, the soil is under consolidation. So under-consolidated soils are rare, but they do happen occasionally. The problem with it and the effect on primary settlement, and your book, I've taken this presentation from my past presentations on the subject. Your book also has one. You look at it too. Your Soils and Foundations manual. Instead of having one knee in the curve, they have 2 knees in the curve. A point where, up to B, which is, say, from this up to B, which is the current, up to the current effective stress, and then they come down. This is a C, this chart calls it C sub R. We normally call it C sub S. I think that this comes from the military. And I know I use many military documents in the past, both in terms of textbooks and as reference materials, and both from all branches of service. And I tell some of my veterans, I'm sure, to whom your service, I'm grateful for your service. And I tell them that with my courses, I use so much of this stuff, it's not like, you register for a course, it's more like you enlist for it. So, but we won't go into that. In any event, the first, it compresses more than it does back here, but not as much. And then it reaches the point where it gets past its past, so to speak, and then it drops down to C sub C like it does with normal cuts. But there's an extra region in here. And then you're going to notice that many times they will take a consolidate, and then they will do an unloading test, which is very common in consolidation test. The main advantage, particularly for a pre-consolidated and over-consolidated soil, is that the C sub R, this is easier to measure than that. In other words, the C sub R, or the C sub S in our terminology, basically it talks about a compression index of a soil that has been already compressed before. This is the C sub C, is the one that has not been compressed before in that range. And it's easier to measure the C sub R on an unloading test than it is in the initial loading. A lot easier. That's one reason why we do it that way. Generally speaking, the C sub S is about 1/6 of C sub C in typical values. And to deal with that, we have two problems. The formula, if we are to the right of point F, in other words, if the pressure is greater than, if sigma plus delta sigma is greater than sigma, in other words, we're over in this range. And it's probably easier to do this graphically. In other words, if we're greater than this pressure, in other words, sigma P, if we're greater than the pre-consolidation pressure, and that's what that's called. This is the effective stress, current effective stress. This is the effective stress in the past for the pre-consolidation. The ratio of these two is the over-consolidation ratio. If sigma naught plus delta sigma, in other words, plus this is over here is greater than sigma P or sigma C, then the S of C, the settlement, is equal to the settlement we get from here to here plus the settlement we get from here down to wherever we stop. If, on the other hand, the stress that we're at is somewhere between here and here, in other words, if the applied stress we've done is within the pre-consolidation, is lower than the pre-consolidation pressure, then we use this formula right here. You'll notice that C sub S, which is this right here, is the only thing that drives this. And that's one of the advantages of being able to use pre-consolidated soils or over-consolidated soils, is the fact that because they have that particle compaction, they will settle less than they would up here, that you blow through the full range of this here and get over here, and they will settle more. And we're going to see this in the following example, because it's about the best way to. We have a soil with void ratio log pressure shown. It's 6 feet thick clay layer under a sand layer. There are two possible additional loads, 5 TSF or 7.5 TSF. We find the OCR and the settlement for each case. And okay, let's start with this one. We start here, and the E naught is 1.05. Up here, this is the initial void ratio, and this goes out to the point here, where at 0.3 TSF, which is the current effective stress. And then from there, the curve goes down into this range, and it goes down to point F. Now, you'll notice that there's a difference between this and the idealized reconstruction and the actual reconstruction, and that is an inevitable result of the way consolidation tests come out. We're always trying to turn shapes like this into shapes like this. We did this with stresses. We do it with consolidation. You get to the point F, and that's about the void ratio has decreased to 0.95, and the pressure on is 6.6 TSF. At that point, it drops like this, and you get this ratio, which you can confirm by laying it out, of 0.42. Then we get to point G and we come back. Now, the main reason why we do that is because we take the slope of this line, and both here and here, you can see the calculations of how you would compute it. It's basically rise over run. The only difference being is that the run, rise this way over run this way. The only difference is that instead of having the two sigmas subtract each other, you take the log of the of the quotient of the two. That's the only difference. Other than that, it's strictly rise over run slope measurement, just like you do in geometry. So in analytic geometry. So that's how you come up with the C sub R for this and the C sub C for that. And you can actually, you need to your own satisfaction, confirm to see that's correct. You can take any 2 points along here or any 2 points along here and make that calculation. My preference is the further you can get the two apart, the more likely it's going to be accurate. Of course, how accurate it is depends on how you lay it out, but generally speaking, you like to get as far apart as possible without getting past the physical limitations. So with that in mind, we've computed C sub R, we've computed C sub C. We know the break point, the two break points of it, the break point between the initial effective stress in the over-consolidation range and the over-consolidation range to the version consolidation range. We know all that. Now we can actually do something with the results. For OCR, is true in both cases, is 6.6 over 0.3, which is basically this over that. 22. That's quite an overconsolidation ratio. With 5 TSF additional load past the overburden, an overburden being, in this case, the effective stress, initial effective stress, 5 plus 0.3 is 5.3. 5.3 falls between 0.3 and 6.6. 0.3 being the current effective stress and 6.6 being the effective stress in the past or the pre-consolidation pressure. We use this formula. In other words, we use, back it up, this formula. And we just plug and chug. C sub S, we're in the C sub S range. We're within the pre-consolidation pressure. And we, the height is 12. Wait a minute, yeah. Hang on just a minute. C sub S is 0.078, which is right here. And, oh, excuse me, height's 12. This is what this is one of my great things I do in live lecture. This is why I do it this way. So I want to simulate the live lecture mistakes and all. 6 feet times 12 inches to the foot. That's 72 inches. And I just plug, get my units straight, and chug. And I get 3.42 inches of settlement. Okay, that's part one. Part two is 7.5 TSF additional load. Now we got a problem. Because with the overburden, the additional load plus the initial is 7.8 TSF. Remember that in all cases, this is the initial load, which is the effective stress load, plus this load right here. Therefore, it's greater than 6.6. So now we're over into this range, 7.898, about here. Somewhere in this area, not too far, but far enough. And then we use this, the longer formula. In other words, this one. And we simply, once again, plug and chug. We've got two parts. On this particular part, you have to put sigma c is that pre-consolidation pressure. Actually, that is the OCR right there. It's the log of the OCR, actually, for that point. And then plus that. I never noticed that before, but that's true. And then plus C sub C, H, and that's just C sub S for this term and C sub H for this term. And we get to, and we do the same plug and chug that we did before. 7.8 is equal to 0.3 over 7.5, and we get 4.75 inches, which is larger than, obviously, that's another over 1.25 inches from what we had before, more than that. So that, in a nutshell, is how we do over settlement calculations for over-consolidated clays. Multiple layers, as I said before, you simply take all the settlements and add them. There's a few tricks you need to keep in mind. Take care to properly the additional vertical stresses, obviously for a finite structure. Unless you've got a one of these infinite surcharges, or uniform surcharges is a better term. Then the stress due to the structure will decrease with depth, as we saw. And you need to be able to compute. You have to compute not only the effective stress, which is increasing with each center of the layer, but you have to compute the structure, which is decreasing, which means that the effect of the structure on the lower layers will be less than it is on the upper layers. Second of all, take care with make sure that you understand the consolidation state of each layer. It may not be the same as it is, so be careful about that. With secondary compression, your Freud calls it the secular effect, and basically, it is after you finish with your primary compression, then everybody kind of sat back and thought, well, we're done with that, so we can breathe easier. Well, just when you thought it was safe, it wasn't. You have another secondary compression. Secondary compression is, and there are, it's a little confusing the way in which your Soils and Foundation Handbooks presents it. Part of the problem is it's confusing the way it's presented, period. Because C sub alpha, which is your secondary compressive index, can either be defined with or without the void ratio, and it's kind of messed. It's complicated, and so. But basically, the difference between this is that this looks suspiciously like the initial settlement. The big difference is this right here, is that this is T2, for which is the time that you finally want to cry uncle on this thing, and T1 with life of the structure, really. And T1 is where the 90% of the primary compression has occurred. As we'll see, there is no such thing as 100% consolidation settlement in theory. In reality, we get 90%. We're, to move into secondary compression, we're ready to declare victory. So let's say we have a data as shown. The primary settlement, and this is secondary. We have as shown. We have a uniform allied load. That's a uniform surcharge of 0.8 TSF. What that means, people, is that at any depth, if you see uniform surcharge, a uniform applied load, what that means, and we've talked about this before, is that at any depth, the change in the load is going to be the same. There's going to be no decrease due to depth. My expected time for primary consolidation is 13 years, and I think I can somewhere go into how that's done. In fact, there may be some stuff back that I think that discusses that issue. E and all is equal to 1 at the beginning of primary consolidation. The clay has it actually give you the the initial effective stress of 0.75 TSF. And we'd like for this structure to be where it is for 110 years. So, and we say C sub alpha is 0.02. find the secondary consolidation settlement. First thing I have to do is I do actually run through the calculations for primary. And you need to go back through this and make sure that you understand what's going on here. Notice that 0.75 is the initial effective stress, 0.8 is what I add to it. Every other calculations are the same, but the bottom line with this, and C to C is given to you earlier, 0.21. You do all the calculations, you come up with a primary consolidation calculation of 6.35. Now, to compute the void ratio, the second thing is at the end of primary consolidation. How do I do that? Well, it's E naught minus delta E. Well, delta E, and you need to go back through to see how I came up with. Delta E is minus, this assumes a normally consolidated soil. If this were a non-normally consolidated soil or pre-consolidated soil, you would have a little bit different approach. But delta E is equal to this quantity right here. In other words, if I were to take this and do a little math with this, I would get this quantity. And actually, I meant this is earlier in the slides. You look at that. That's how you compute the log rate. Instead of having all this, you take this term out and this term out, and you're left with that. That's your void ratio change right there. And I simply plug and chug that. I get 0.93. In other words, it's gone from 1 with initial to 0.93. By the way, if you happen to have the if you happen to get to where the final void ratio is higher than it, you've done something wrong. Then I do a secondary compression calculation. I simply say that C sub alpha, which is given, H, which is given. I don't usually worry about the fact that I've decreased the height. Usually I don't. I could, technically I probably should, but I don't. 1 plus E sub P, which is the void ratio going into secondary consolidation. I simply assume that it goes full, I get the full thing. In other words, I know this says 90%. I simply use the initial void ratio at full consolidation times the log of the final time, which is 110 years, over the log of the time that goes into that, which is 13 years. And I get 1.84. So the total compression, because of the two consolidations, is equal to 8.19 inches. And that finishes settlement for cohesive soils. We're going to talk about Huff's method. Now, Huff's method dates back to the 1950s. And it is, there is some, I would say, controversy, but actually there's very few methods we do in soil mechanics, including the one we just went through, that have no controversy at all. By the way, as just an aside before we get into this, I'll mention the fact that back a few years ago in Geostrata, which is the Geo Institute's magazine, an article by Jean-Louis Briot, who is now our ASC president. And he discusses, the settlement of the San Jacinto Monument. And when he does, he unleashes one of his pet peeves, the fact that we actually don't compute consolidation settlements the same way we use with other types of elastic settlements, with using some kind of modulus elasticity. And I actually responded to that. Verreut kind of dances around that subject, because I think it may be one of Verreut's pet peeves as well, or one of them. And but in any event, I actually responded to Jean-Louis' piece, and it's on my website. You can look at it. And basically, what the problem is that in consolidation settlement, we can use the modulus elasticity to do it, The problem is that the modulus of elasticity, and if you rearrange some things and you look at the way that the test run, the modulus of elasticity actually increases as we apply further pressure. The problem is not that we can't use just the modulus of elasticity itself as a moving target. And we can also show, and I do it elsewhere, that the modulus of elasticity of a soil, or the shear modulus of a soil, and by extension the modulus of elasticity of the soil, is related to its void ratio of porosity. In other words, as void ratio of porosity drop, the modulus of elasticity increases, which means that the whole thing kind of hangs together. I agree with him that it's not a very consistent way of doing it, and I think eventually we're going to get to the point where we're going to be able to do it differently. In the meanwhile, however, we're doing it this way. I think eventually I think he's basically right that it is a problem, but it's a problem that is going to, I think, will eventually solve itself when we get more deeply into the whole relationship. We've actually the whole business of the void ratio and porosity versus the modulus of elasticity or shear modulus goes back to the 1960s when Bobby Hardin at the University of Kentucky started looking at the problem, and we've come a long way since then. So that's a promising field of soil mechanics. But that, I digress. All right, the Huss method uses the same principle, but it applies the math a little differently. And your manual has a nice description of it. It tends to be conservative. I think the conservatism that is in Huss methods is, and I'll explain why I think it may need some further emendation. I'm going to show it to you the way it's presented in the book, but I think that I will explain what I think is the problem. Okay, the method, and they go to blow by blow. You subdivide into the subsurface soil process into approximately 3 meter 10-foot layers. I told you that the layering of the soil depends upon the changes in the soil as it goes down. You change soil types, you change layers, but you can also subdivide those into more layers. You can always use more layers than you have to. There's less layers where you get into trouble. Then you correct your blow counts to an N160 value using the methods we discussed earlier. Determine the bearing capacity index using the corrected SPT blow counts. Calculate the effective vertical stress at the midpoint of each layer, just like you do with the clays. And then you can the increase in stress, just like you do with the clays, for using the 2-to-1 method. For this course, you use 2-to-1. You could also use boosting this if you wanted to. Calculate the settlement in each layer using this formula. This formula looks suspiciously like, except that instead of having this C sub 1 plus void ratio, we have the C prime. The same construction we had with Varroy. And actually, the C sub prime here and the C10 for Varroy are basically the same. The only difference is, in this you've got epsilon. Well, S over H is equal to epsilon, so you split it up and the settlement is equal to that. That's the difference. It's the same idea. I think, now there's 2 tables we have here. One of them is, this is the one given in the Soils and Foundations Handbook. This is the one that comes from Varroy, and the C10 values are the equivalent. And you'll notice that in a vague sort of way that they're in the same ballpark. And you'll notice that the sands have a higher C sub prime than your silts, and that's likewise in Varroy's table. I would use this one. I think what's happened to Huff's method, and I'm not going to go into trying to fix it. When Huff came up with the method in the 1950s, had not really gotten into the whole issue of correcting SPT values the way we do now. And I'm not sure that somewhere in updating the method for modern SPT values that we've lost something. And that may be why the results are so highly conservative. Correction factor for blow counts, the same we had before. I'm using this formulation, is the one that I use. I think it's the Lamb and Whitman formula. I'm not sure. Let's take an example. Clean, well-graded, fine to coarse sand layer above the clay layer at the surface. N60 is equal to 20. It's 35 foot thick. The unit weight of the soil above the free surface is 110 PCF. The submerged unit of soil below the water table is 65 PCF. The depth of the water table is 15. Building placed on the surface, which is kind of unusual, but makes for a simpler problem. It's a square foundation. The total load on the foundation is 9,000 kips. Find the average settlement of the building due to the settlement of the sand layer. Step 1, compute the effective stress profile, and that's what from here over to here is all about. That's what that's about. We're using unit weight of the soil, all this good stuff. We're using a submerged unit weight approach to the problem. We're not using total stress minus per water pressure approach. Now, we have the loads from the stress from the foundation. Now I'm going to use layer 1 as an example, but the calculation's all the same methods. I compute use a 2-to-1 method for layer 1. The delta P due to the foundation is this formula. Again, this is taken from what we've done before. We're doing it again. And I end up that the stress increase in the first layer is 6,400, but you'll notice as we drop down here, it decreases. Second, correct the SPT overburden pressure. Same method we used before. I'm just going to do it for layer 1. I have the average effective stress in the layer, which is also what I use to correct for, I use that for, I've used the same method that I used before to correct for the same value I used for the middle of the layer for the effective stress. I use that to correct the SPT blow count. So I do the same thing. I go through this formula right here. I end up with this, which is 30, and N160 is equal to 31. And then layer 2 is different because, again, because you have a whole different effective stress, you have an entirely different effective and a different blow count as well. Well, you normally have in this particular case, we're using the same blow count for both of them. That's not necessarily the case. The two layers can have different blow counts. And then I use this divert method for C for the first, for the first layer. I start with 31. I come up and I come over and I get about 90 thereabouts. The second one is 19. I come up and over and I get about 65. Those are approximate. And I get C sub prime values are shown actually 90 to 65. How about that? I actually read my own chart right. That's an improvement. So I have layer 1. I use Huss method. I just plug and chug once you get it set up. See, that's a lot of these problems. Setting them up is the tricky part. The plug and chug, once you get it, if you set it up right, the plug and chug comes out right. So H naught over C prime. H naught is different in both cases. C is prime is different in both cases. The sigma naught is different in both cases. The delta sigma is different in both cases. But you get up, the first layer is 1.88 inches and the second layer is 1.33 inches, and you add the two together and you get a total settlement of 3.21 inches. And that, in a nutshell, is Huss method. Now we come to the time rate of consolidation. And we want, the question of how long is this going to take is one which students ask on a regular basis for all kinds of things. How long is he going to talk in class? How long is this test going to be? How long is this? How long is that? Well, how long is an important topic, and then we're going to talk about that. And I've got some definitions there. This also from your Souls and Foundations handbook. They do a fairly decent job of presenting consolidation and settlement. Consolidation is a process that takes place over time, results of two processes: the dissipation of the excess pore water pressures and the rearrangement of the soil skeleton. Do some assumptions. I'm going to discuss both of those. Plain water system is homogeneous. In other words, it's the same void ratio, same specific gravity, same everything. Saturation is complete. This only applies, this is for clay soils, completely saturated. Water is incompressible. Vroit kind of throws a few trouts in the milk for this, but we're going to stick with that assumption. Soil particle is incompressible. Flow is in one direction only, which is basically up and down. And Darcy's law is valid. Basically what's going on here is this. I apply a load, Q per unit area, and basically I'm applying it on a clay layer, usually a loose clay layer, and the clay layer is has a lot of voids. Now what happens when that happens is that the water will initially take the load, but then the water decides it wants to bail out on you. Kind of like a lot of your group projects. You've got a team member that comes in, and initially they're all fired up about it, but after they see they get under pressure, they're ready to leave. And that's pretty much the way it is with water. It wants to leave, and it does leave by whatever path it can find. And we're going to talk about how important knowing what that path is. And so therefore, once the water leaves, the void ratio decreases and it settles. But that's not an instantaneous process, because the clay particles, being small and compact, being what they are, don't want to give up the water without a fight. And that fight can take months and years. So we start out with an arithmetic pressure void ratio. Up to now we've looked at, we start out with the A sub V, which is the arithmetic, which is delta E over delta P, which, for an elastic sample is constant. It's the only thing we worry about, but we don't. And we go through a lot of math, and I'm not going to really explain much about this math other than to say that this can be used in certain situations, but it basically gives us a relationship between the void ratio and between time and distance. And of course we see the decreasing porosity relationship, and we do some substitutions and rearrangements. The key variable here is M sub V, which is the coefficient of volume compressibility. But basically, in the midst of all this, we've established a relation. We've brought time into the equation, which we didn't have before. But the time to do it is determined by Darcy's law. So we pick up Darcy's law. We do some differentiation and equating and rearranging. And we end up now, we've got permeability in the mix. We've got the volume compressibility in the mix, and we're ready to do some more rearrangement. And we end up with this equation. which is very similar to the heat equation, and we consolidate, pun sort of intended, we consolidate the volume compressibility, the unit weight of water, and the permeability into what we call the coefficient of consolidation. It's the key variable. This equation here is very similar to the heat equation, and something that Terzaghi recognized when he actually came up with this in the early 1920s when he was teaching in Turkey. And he and now we've got an equation that relates how long it takes to how much it deflects, because U is of course the deflection, displacement. Now some of you are looking at this saying this could get bad. Well, like I keep reminding everyone, one of the reasons why certain engineers go into geotech is because their math skills aren't the greatest and they want to do something other than make fancy calculations. And I'd be the first to admit that solving an equation like that is not something that most civil engineers do on a regular basis. Fortunately, we've made it easy for you. But first we have to make a statement. This is a partial differential equation. And partial differential equations have two things. All have two things. They have initial conditions and boundary conditions. To solve any partial differential equation, you have to understand both. Let's start with the boundary conditions. And the boundary conditions are we're going to do both. There are two ways of looking at this. First of all, let's look at let's start with the boundary conditions. The boundary conditions in this particular case are literally at the boundaries of the system, which is the top of the layer and the bottom of the layer. How about that? And they are, to keep things simple, we like to make them simple Dirichlet type conditions. And Dirichlet was Felix Mendelssohn's brother-in-law, and if you can get Dirichlet boundary conditions, then you're in good shape. A lot better shape than you are otherwise. Either we assume that a layer above is pervious or below, or impervious. Now, we have two different conditions we consider for boundary conditions. One, both layers are pervious. This is called double drainage. The other one is one is pervious and one is impervious, and that's single drainage. Now you say, well, pervious, impervious. Pervious, that's a relative term. I'd be the first to admit that, but I also showed you in permeability that permeability can vary and does vary between soils by several orders of magnitude. If you've got a clay layer with a sand layer above it and rock below it, it's pretty easy to say that for practical purposes, above is pervious and below is impervious. And basically what it means by pervious is that for the excess pore water pressure can go to zero at the boundary, and then the rest of the layer gets the message sooner or later, and it starts dropping as well. In the case of one pervious layer, only one boundary gets the message, and in case of double drainage, both boundaries get the message. There's only two of them. Okay, so that's the business behind, and that's important. That's very important, and we're going to incorporate that in a very simplistic way into these equations. And for the other condition, the initial conditions usually mean the distribution of pore water pressure from one end to the other before all the action starts. or at the time the action starts. Now, there are a number of ways of, there are a number of distributions, and you can see them. You have a triangular distribution, a parabolic distribution, all kinds of distributions. Most of the calculations that we use for the standard consolidation tables and equations and whatnot assume a uniform pore water pressure distribution. In other words, when the pressure comes, all the pore water is equally affected. And then it starts heading for the exits. So uniform, which is so it's a uniform assumption, and that's just built into it, and we're not going to discuss that any further. But that is the assumption behind most of them. So how do we solve it? Well, I'm not going to go into this very deeply other than to say that if you're interested in this topic, Verreut's got 2 chapters on it. He solves it using closed form methods, and he also uses a numerical method. And you'd be more than happy to investigate that. But the bottom line is this. Now, I said that, we don't like fancy equations. So what we do is we do 2 things to deal with the tricky part. Of course, is the boundary conditions and whatnot. First of all, we're not really interested from a practical standpoint in tracking the decrease in pore water pressure. I mean, it's important, but it doesn't really tell us what we really want to know. What we really want to know is how far does this thing go? And so we define the little thing called the time factor. And the time factor is equal to the time of consolidation from the time of the initial loading. We assume instantaneous initial loading. C sub V, we talked about that. HDR squared. Now, this is where we pick up the boundary conditions. The drainage length is the longest distance from any point in the layer to where the exit is. In the case of single drainage, it's the full thickness of the layer. In the case of double drainage, it's half the thickness of the layer. That's an easy place to screw a problem up. And I'd be the first to admit it, but it's important. That's a crucial thing. If you mess that up, you've messed the whole problem up. Fortunately, it's usually most problems are defined. It's usually pretty easy to figure out, but don't miss it. Basically, the concept is that the soil is that basically it's kind of like walking through the woods. You get to halfway of the woods, you're halfway in or halfway out for double drainage. The table on the right side of this is really where we take this mess and simplify it down to something we can use. On the right column is the time factor, which you compute using this equation. On the left is the degree of consolidation. Well, what is the degree of the degree of consolidation? Very simply, is I'm probably going to go ahead and I'll just leave it here. The degree of consolidation is the percentage of the total consolidation settlement that we've actually achieved. So, for example, if my calculations show me that my settlement is going to be, say, 6 inches, then 50% consolidation means it's gone 3 inches. And that tells me how, and using to that time factor, T sub V for 50% is 0.197. That means that I can take that, I can substitute into there, and I can rearrange and get the time it takes to get halfway through the consolidation process. So that, in a nutshell, is degree of consolidation. Degree of consolidation is also expressed as a function of the pore water pressure, as well as the degree of pore water pressure in addition to the distance. So the two are related, We're more interested from a practical standpoint in the degree of consolidation, the pore water pressure, but you should be aware of the fact that pore water pressure is decreasing, or excess pore water pressure is decreasing as this consolidation process goes along. And this is a nicer little curve which shows the table or a curve, and you can see both. The tables are a little easier to read, and if you're using the exact value, this table is a little different, but the results are the same. So, example of time factor calculation. We've kind of gone through this. As shown, same problem we had before. E sub null is 1.0, C sub C is 0.021, C sub V is 0.03 square feet per day. Find relationship of time of consolidation with time factor. Usually speaking, I won't make you go through the whole 9 yards. What I'll usually do is say, I want to know at this time, or maybe this time and this time, or something, 2 or 3 times at the most. So T sub V is equal to that, and we set it up, and we say that T sub V is equal to T over 2130 days. We simply substitute. Now notice carefully, notice that and it's not really clear, but this is sand and this is sand. Since it is sand, I have double drainage. Which means that this is a 16-foot layer, but however, my drainage length is only 8 feet because of double drainage. So I put HDR is equal to 8 and 0.03, making sure my units are consistent. You all should make sure units are consistent. T over 2130 days is equal to T sub V. What I do is the following. I simply say that what I do is for this table over here, I'm pointing to me. We have days. I set up a number of days, which is, until I know what I'm doing, it's arbitrary. Of course, some of you are saying that never happened, but I have days, then T sub V is equal to the time, that days over 2130. I get T sub V out of that. If I have T sub V, then I can compute from the tables, and there are also some equations that you can use. I think they're buried in, I think Voigt may have some of them, is equal to the percent consolidation. I translate from T sub V through this table right here, and I get percent consolidation. And then I get settlement. So therefore, after 1,000 days, for example, I am settled 4.76 inches because I'm at 75% consolidation. 75% times, and my original, if you recall this problem, my original primary consolidation settlement is 6.35 inches times 0.75 is equal to 4.76. I simply am taking this times this to get that, in other words. And the solution as given is that in graphical form for this series of problems I've used. It came from DM7. For a multi-layered system, we just add the settlements. Consolidation is a little more complicated. If I have 2 layers next to each other, I can combine them into one layer, say 2 clay layers. I can combine them into one by applying this method. I don't present this very often, but there it is. The coefficient of consolidation. I normally leave this problem, have traditionally left this problem for the lab. It's not an easy thing to do for the first time student, but there are 2 methods that are used. One of them is Tersagi's logarithm of time method, which has been modified by different people. and the other one is Taylor's square root of time method. And I think both Verroit and your Soils and Foundation Handbook discuss this in some detail. Now, some of you are sitting there thinking, who's got time to wait for this? Let me assure you that some of your clients have thought the same thing. And so we're going to talk about how we speed it up. I mean, you know, the previous example, 7% sell in 1,000 days, or which is 2 years, 8 months, 23 days. That's a long time for everybody to sit around waiting for something to consolidate. Can we speed it up? The answer is yes. The way we do it is by tricking the soil into thinking that its permeability is high. And we do that by providing a high permeability path for the water escape. And we not only provide a high permeability path, we provide it in lots of places to reduce the distance that it has to travel through the low permeability stuff to get to the high permeability path. And that way we can reduce the consolidation time. And the classic way of doing that is vertical drain system. Vertical drain system looks like this. Basically, you've got drains, usually wick drains, sometimes sand drains. There are a number of ways of doing it. And they're driven into the soil at regular intervals, in sort of a grid array. And what that does, instead of the water having to start from, say, here in the middle, go all the way up here or all the way down here, it just goes from here to here and then it shoots out. And then you collect the water at the surface through this drainage blanket, which is basically a layer of sand or gravel, and you drain it off. You have observation wells to keep track of the facilities, and most of also you have this big surcharge. If you're going to speed consolidation up, you really want to speed it up. And the way to do that, if you remember consolidation equations, you'll get more settlement, and by increasing the pressure you put on. So you put lots of pressure by putting lots of stuff on top of it, and you get accelerated drainage. And then when you're drained to your satisfaction, you can take the berm off and the surcharge off, and then you're good to go. This is some common types of vertical drains. The classic type of your sand drains. This process developed, I think, in the 1930s, and basically where you actually create, usually using corrugated pipe of some kind, you drive in and then you put sand in there, and then you can use, and then the pipe goes away, and then you can use those. That's where and then you use those to pull the water out, or push the water out. It's more accurate. Push the water out. That is classic. You still see that sometimes, but sand drains are a real pain to put in unless you just absolutely have to. A more convenient and a result of geosynthetics are wick drains. They are used, instead of using sand columns, you use wick drain. They're basically a cloth geosynthetics, or I think sometimes called paper, but usually a cloth of some kind. And they are pushed in the ground using a mandrel. And basically, a mandrel is basically you take the cloth, you attach it to one of the mandrel, you use the stiff mandrel, steel or something to push it in the ground, then you withdraw the mandrel and you leave the wick drain in place. And then the wick drain acts in the same way as the sand column did, by the water coming to it and then easily getting it out of the ground. And you do this, as you see here, in this nice regular array that you have. They can be installed, if you can push them, it's the easiest way to do it. Occasionally you'll run a situation where it's not going to work, where you're not going to be able to push them. You're going to have to vibrate them. And I've been involved in that particular application. It's very hard on the equipment, but it's very effective to accelerate drainage. And in very low permeability soils, and very thick layers of those low permeability soils, it's almost a necessity. So, and that's consolidation. We've covered a lot of ground. It's an important topic. So until next time, thanks for watching, and God bless.